Apologies for slight delay. Welcome to the last class. I hope you all appreciated how useful the previous class was in the talk yesterday afternoon. If you noticed that exactly the things we talked about came up. It was very good. And then this, just now again, you saw this lemma about finding an edge between two sets. So I don't know if we're going to get as lucky again. That was not planned. It was just luck. But anyway, so I'm going to tell you about dependent random choice. Okay. So to motivate this technique, I'm going to talk a little bit first about something called the Ramsey-Turan numbers. So definition. The Ramsey-Turan number is RT of n, h, k. Okay, so n is a number, k is a number, h is a graph. Is the maximum number of edges in a graph such that the graph is h-free with n vertices, and the independence number of the graph is the most k. So why are these called Ramsey-Turan numbers? Well, if you ignore this condition, this is what's known as the Turan number of a graph, the maximum number of edges in an h-free graph on n vertices. If you ignore this one, this is basically the Ramsey number. You're looking for, if you're not looking at the maximum of edges, but you're saying that in the complement, you're happy to have a large clique. You're sort of looking for either a copy of some graph or a large clique in the complement. This is a problem that sort of combines aspects of extremal graph theory and Ramsey theory. Okay, so just to get some feel for what this is, let's look at the case where H is a triangle. So, who can give me an upper bound on the Ramsey-Turan number of the triangle? Okay, so we've got a triangle-free graph, and we know something about its independence number. Good. So what's the nice property of triangle-free graphs? Yeah, the neighborhoods are independent, right? So all we have to do is pick a vertex and look at its neighborhood. And what you tell me the neighborhood, it's independent, so our size at most k. Right? The neighborhood is independent set. Okay? So now, what bound can you give me? Yeah, exactly. Every degree is at most k. Sum the degrees, you get k times n. So the number of edges is at most k n over 2. This is actually sharp for some values of k. It's not known exactly when it's sharp, but it's quite often at least close to sharp. Okay, so that wasn't very interesting. It was kind of easy. Okay. H is K5. So I skipped over K4 for a reason. We'll come back to it. Give me a construction of a K5 free graph with lots of edges and no large independent set. What would you do? Well, what's a good way of putting lots of edges in a graph without creating cliques? Yeah, right? And we just want lots of edges. So it's enough to just put, say, a complete bipartite. Right? Then we're really not even making triangles. Okay, that's good. We've got lots of edges. We haven't even made a triangle, but we have these large independent sets. So we have to get rid of these large independent sets without creating a K5. How should we do that? Yeah, so what do we want? The edges we add inside, what property do we want? We want to add in some edges, maybe randomly, so that we can put some graph sort of H, we'll call it H, I don't know, G prime here and G prime here, such that the independence number of G prime is at most K, is small, and what do we want to avoid? Well, we definitely want to avoid a K5, but if we have a K4 here and a K4 here, then we've got a K8. That's bad. We're at K4, then even just one vertex added is going to kill us. So what should we actually avoid? What's it enough to avoid? A triangle. If G prime is triangle free, then the whole graph is K5 free. So any K5 by pigeonhole has 3 vertices on the same side. That has to be a triangle. Okay? So if we can find a triangle-free graph with independence at most K, then we're happy. When can we find a triangle-free graph with independence number at most K? Exactly when? Sorry? No. So this is telling you the number of edges in a triangle-free graph. I'm saying, so we want to find any triangle-free graph. We've already got all our edges, right? We're not really bothered how many extra edges we get. It's going to be relatively few. But when can we do it at all? When can we find anything? What does it mean for there to exist a graph G prime that's triangle free? It's exactly the Ramsey number 3K. This exists if and only if the number of vertices of G prime, right, the number of vertices on the side, this is n over 2, n over 2, exactly if, I've lost my eraser, there it is. Is at most R3K. Right. So this is at least n squared over 4 if n is at most 2 times R3K. Okay. And R3K, what do we know about it? Well, we know it's sort of between it's between n to the k to the 3 over 2 and k squared, right? That's what we proved so far. Okay, so as long as k is sort of satisfies this property, then this is really big. Okay? And it turns out, though I'm not going to prove it today, lack of time, that this is true if also k is much smaller than n. So this is giving basically the correct behavior when k is in this range, much smaller than n, but not too much smaller, at least like root n or n to the 2/3. Okay. Okay. So that's nice. So this one, when k is little o n, is little o n squared. This one is order n squared over, n squared over 4. Okay. And this is true for all, if you increase this 5 to something larger, this lower bound is still going to hold, right? As this number gets bigger, this also gets bigger. So this leaves us with a case of K4, which is actually quite a bit harder. Okay. So it turns out, I'm just going to tell you the theorem. Proved by Semeradi, one bound, and Bolovash and Erdush, the other bound, in the 70s, that Ramji-Turan of K4K is n squared over 8 plus little n squared if k over n tends to 0 slowly. Okay, so if your k, you're not allowing linear size independent sets, you say the independent sets have to be little o n, then there exists some graph with this strange property, and that's actually best possible. So this is a somewhat more difficult theorem. One bound uses Semeradi's regularity lemma. The other is a very clever construction involving high-dimensional spheres. Okay, so let's not talk about that. I want to talk about what happens if we make k a bit smaller. If we say, okay, if k over n goes 0 slowly, then this construction exists. What if k over n goes 0 faster? Okay. Can we show that actually this thing is little o n squared? So that any graph with positive density has and small independence number has a copy of K4. Okay, so here's a theorem I want to prove. So the Ramji-Turan number K4K is little o n squared if k is at most, let's say, n to the 1 minus epsilon. Okay, so let's take a deep breath and understand what the statement says. So what it's saying if you have a graph with no independent set bigger than n to the 1 minus epsilon is some small constant, and epsilon n squared edges, so positive density, it must have a K4. Okay? And this construction that I didn't show you shows that you can't really make this much bigger. Go ahead.
I think it is a dumb question, but what does it mean formally to say slowly?
So there are some particular bounds. Yeah, so this doesn't mean, so I guess this is true if this happens sufficiently slowly. And yeah, so right, there exists some function which, if it's going slower than that, then it's true. In reality, it works down to, so its k is little o n, but I think it's greater than like e to the minus root log n times n, something like that. Yeah, so this is the real behavior if you do the calculation very carefully. Yeah, I mean, I was stating as a weaker version. It's just if it's a n divided by log n or something. Right. Thanks. More questions? Okay, so we have this slightly strange statement. How can we prove it? Now, here's the idea. Suppose we can find a set A in our graph G. Maybe let me stay what we're doing. Okay, so in other words, so we're going to restate this theorem in words. If the number of edges of G is at least epsilon n squared, and alpha of G is at most n to the 1 minus epsilon, then G contains a copy of K4, contains a clique on 4 vertices. Okay, that's what we're going to prove. Does it make sense? Right, so epsilon n squared is nowhere near enough to find even a triangle, right, in an arbitrary graph. But saying there's no large independent set is forcing us to kind of spread the edges out everywhere, and that somehow is going to help us to find this copy of K4. Okay. So here's the idea. Find a set of vertices in the graph with the following property. Let me draw it here. Here is A. I would like A to have the property that, such that, the size of A is bigger than K, has more than K elements. And if we look at any pair of vertices in A, and look at their common neighborhood, that also has size bigger than K. Bigger than K for all U and V in A. Suppose we can find this magic set. Why are we done?
Does the common neighborhood outside A have to be bigger than K? Or
No, it can be any. It can be anywhere. It can intersect A. Yeah, so I've just drawn it there.
The neighborhood of A can't be an A intersects.
Right, that's true.
So
So,
it would be an edge,
yeah.
obviously
With what?
the neighbors in A.
Right. So first, A is size bigger than K. Independence numbers are most K, so A contains an edge. Call the edge UV. Because every pair of vertices has large common neighbor, this pair does. So we can choose U and V to be an edge. Look at the common neighborhood. That's also big in the independence number, so there's an edge. 1, 2, 3, 4. We found a K4. Okay? So if we can find this magic set, then we'll be very happy. Does it make sense? Okay. So now I'm going to show you how to find this magic set actually in much more generality. Okay? And the much more general version will have, not just imply this, as many other applications. So we saw one, well, we didn't quite see it, right? One was mentioned in one of the talks, in the talk this morning. Okay. So, what are we going to do? Okay, I'm going to prove what's called the dependent random choice lemma. Okay, the statement may look initially a little bit confusing. We're going to prove it. The proof will make it make more sense. And then, when we apply it, hopefully make even more sense. Okay? So, the aim is to find a set with these properties. But we're going to state it in more generality. So, let A R S maybe be any integers. So if some property holds to do with the number of edges of the graph, so I'm not going to say what it is, but till later, something, then there exists a set of vertices such that the size of A is at least A, and every S set in A has at least R common neighbors. Okay? So we're not just going to find a set A for every pair of vertices has many common neighbors. We can find any S set as well. Okay? So this will imply the thing we want, assuming we have enough edges. Okay. Right. How are we going to prove this? So this is a deterministic statement about graphs, right? And this is a course about the probabilistic method. And I'm calling it the dependent random choice method. I mean, okay, we're going to use randomness. But there's no randomness here yet, right? This is a bit different from previous things we've done. When we said, okay, we want to show there exists some object, some graph, some coloring, so we choose it randomly. Here we're given our graph, and we have to find this subset. Okay. So the first thing you might think is, why don't we just choose the elements of A randomly? But yeah, unfortunately that doesn't really work. We don't really have any control over these common neighborhoods. So we have to do something a bit cleverer. Okay, so here is how we're going to choose the set A. We're not going to choose the elements independently at random, as we have basically every time before. We're going to choose it randomly, but depending on the structure of the graph G. So here's the proof. So let V1 up to Vt, say, be independent, uniformly random elements of the vertex set. Okay? So we pick T independent random vertices. Right? Because they're independent, we could pick the same vertex twice. Okay? I'm not saying it's a set of size T. You just T times pick a random vertex. Okay? And let's let T be the set V1 up to Vt. Okay, so we've got a set of at most T vertices. Okay, so our first attempt at a set A is going to be the common neighborhood of these T vertices. Here are the T vertices, or most T vertices. They have some common neighborhood that I'm going to call N of T. So this here is the intersection over V in T of the neighborhood of V. Okay? This is our first attempt at A. It's not going to be our final attempt. We're going to have to change it. But it's our first attempt. Okay? So why is this a good idea? Why is it a good idea to try this common neighborhood? Well, we would like vertices in our set A such that the pairs, the small subsets, have many common neighbors. If there's a pair of vertices, let's think of S as being 2, so a pair of vertices with small common neighborhood, are we likely to pick it in this set? Well, no, because you have to pick all of the vertices of T inside its common neighborhood. Otherwise, it won't be there. Right? So we're picking a set of points whose neighborhoods have to be, common neighborhoods have to be large. Right? Otherwise, we wouldn't have picked them together. Might pick one or the other, but not both of them. Okay? So we're picking the set T uniformly, but the set A we're trying to find has this strange distribution depending on the structure of the graph G. Okay, let's see why this actually works. Okay, so first thing we want the set to be big, right? If this is going to be our A, we need to have size at least A. Okay, so let's look at the expected size of this common neighborhood. So X is the size of the common neighborhood. What can we say about the expectation of X? Maybe I'll do this over here. Okay, what is the expectation equal to? The expected size of some set. So it's the sum over vertices of the probability the vertex in the set. Okay, that's easy enough. Sum over all vertices of the probability that V is in the common neighborhood of T. Okay, but T is the random set and V is just some vertex. So I'd like to rewrite this in a more useful form. So here's T and here's V. V being in the common neighborhood of T is the same thing as T being in the neighborhood of V. Right? Those two things are the same, just look from the top or the bottom. This is equal to sum over vertices, probability that T is contained in the neighborhood of V. Okay, that looks better. What's that probability? The neighborhood of V has size degree of V.
Can V choose T over N choose T?
So close. So remember that we're not picking a random set of size T. We're picking T independent vertices that they can repeat. Exactly to make this calculation slightly easier. Yeah. So it's almost that, but something slightly simpler.
T over N to the power of.
Exactly. So each to the power of T. Exactly. Right? Sum over V. The degree over N, that's the probability each VI is in the neighborhood of V with probability exactly degree of V over N. And then there are T of them, and they all have to be in. And they were chosen independently. Okay, so that's a slightly weird expression. How do we deal with expressions like that? Convexity, right? X to the T is a nice convex function. If you're summing a bunch of some convex function, then it is, what do we want? When it's minimized by taking all the values equal. Right? You minimize sum of x squared, sum of xi squared by taking everything the same. So what you get is n times the sum of the degrees over n to the t. Make sense? So this is the average degree is the sum of the degrees divided by n. If all the degrees equal to the average degree, then that minimizes, so that minimizes this sum subject to the sum of the degrees, right? Which is just twice the number of edges. Right? So let me simplify this here. So the sum of the degrees is twice the number of edges. Divided by n is like divided by n squared. And there's an n outside. So we get 2 times e of g to the t over n to the 2t minus 1. Okay, let me just write it in a slightly cleaner way. Over n to the 2t minus 1. And this is convexity. Okay, so just Jensen's inequality or whatever you want to do. It's, sums of convex functions are minimized by taking everything the same. Okay, so we got something. Okay, so it looks a bit weird. Okay. But we also want every S set to have many common neighbors. So we want no S sets with few common neighbors. So what do we always do? Count the S sets with few common neighbors. Right? Just the same as always. Okay. Yeah, maybe I'll do this again afterwards. Okay, so let's let y equal the number of S sets in A such that the size of the common neighborhood of S is less than R. Right? And we would like this to be 0. Right? If it's 0, then we're happy. Then we can just take A to be n of t. Okay. So what can we say about the expectation of y? Well, it's the sum over S sets in A of the probability that n of S is at most R. Is that right? Is it right? They're nodding along happily. No one has complained yet. This is a test if you're awake or not. So no, this is silly. I'm writing something silly here. Right? Where's the randomness? Sorry, this is n of t. Not in A. Sorry, there's no A. Right, the randomness is in t. This is not a random thing. Right? It doesn't make sense to say the probability of this. Right? This is just some set S. Okay, the randomness has to go here. It's sum over all S sets S with this property of the probability S is contained in n of t. Right? It's sum over all S sets which have few common neighbors in the graph, or the probability that we happen to pick the whole S set. Right? And that's what we said at the start was if a set has few common neighbors, we're unlikely to pick them all in T. Right? Now we're going to use that again. So here's T, here's S. When is S in the common neighborhood of T? When you have all of these edges between S and T. Right? That's when it's in the common neighborhood. That's the same thing as T is contained in the common neighborhood of S. Right? It's just exactly the same thing as the sum over the same stuff, the probability that T is contained in the common neighborhood of S. Right? Just by from the picture. Right? They both just mean you have all the edges between S and T. Is it okay? Look extremely unhappy. And no one is complaining. If no one complains, then I speed up, so you need to complain. Okay. I hope it's clear, just by the picture, right? They're just the same thing. Now, what is this probability? What is this probability? Yeah, right, the common neighborhood has size at most R. So it's at most R over n for each vertex in T to the power T. And how are we summing over, in the worst case, n choose S sets. Okay, so what have we got? I'm now going to write the correct statement. And now hopefully you'll see it won't seem quite so confusing. So if 2e of g to the t over n to the 2t minus 1 minus n choose s r over n to the t is at least a, and what is t? We get to choose it. If there exists a t such that this holds, then we have our conclusion. Okay. Now, everything's in place. Tell me how to prove the lemma from our two calculations. What should we do? Yeah, exactly. So, we took our random set T. We looked at common neighborhood. The expected size is this. And the expected number of bad sets is this. And the difference is at least A. So if they have their expected size, then we can afford to remove one vertex from each bad set and get a set that we like. Okay, but that's an expectation. How do we make it precise? Well, what we care about is x minus y. So why don't we just look at the expectation of x minus y, which is equal to the expectation of x minus the expectation of y, which by our two calculations and our assumption is at least a. Is it okay? Right? The first step is linearity expectation. The second step is that calculation and our assumption. It's okay? Yep?
I think you still have to say that there's an instance where x or y is at least or close to the average.
Exactly. So now, because the expectation is at least a, this implies that the probability that x minus y is at least a is positive, right? By the same thing we were doing right from the first class. Whatever your expectation is, you always achieve it for some outcome, right? So that is, in other words, there exists a set T such that for that particular value of t, x of t minus y of t is at least a. Right? Take that value of t, look at that guy's common neighborhood. It has size x of t. It has y of t bad sets contained inside of it. Remove one vertex from each, you destroy them all, and you still have a vertices left. Right? Remove one vertex from each of the y of t S sets, in N of t with common neighborhood S and R. And we're done. Okay? So I want to show you this partly because this is a very powerful tool with lots of applications, but also because this proof technique, you see, it's very useful, right? It's a very kind of simple idea. Just this part here, it's a very simple idea, but it's very powerful. Okay. So it's a little harder than the things we've done so far, but not too hard, right? Okay. Okay. So, how are we doing for time? Let's try to deduce the theorem we had before. So the theorem, Ramsey-Turan number K4K is little o n squared if K is n to the 1 minus epsilon. Proof. Okay, tell me how to prove it. All of the pieces are in place. Yeah. Exactly. Yeah. Yeah. I was hoping everyone was going to be jumping up and down saying that. Okay? We just apply the lemma. We just need to check there exists a t that works. Right? So what did we say? We said that we wanted to find a set A has to be of size bigger than k, such that every pair of vertices has more than k common neighbors. Right? Okay, so we're going to apply this lemma with what values? We need to pick A, we need to pick R, we need to pick S, we need to pick T. Sorry, maybe I'm going to change the definition slightly so that I only need to find at least k. Sorry, I should have done that in the first place. So the definition of this is now strictly less than k rather than less than or equal to k, just to avoid me writing plus ones everywhere. Okay, tell me, what should A, R, S, and T be? You just pick one of them and tell me. Shout out. A is k, yes, very good. Excellent. S is 2, very good. R is k. And now we just need to figure out T. Okay, so let's try and figure out T. Need to figure out a T that works. Okay, so we've got our equation. So what have we got? So the number of edges of G we're assuming is E of G is at least epsilon n squared, right? And K is n to the 1 minus epsilon. So let's plug it in here. We have 2 epsilon n squared to the t over n to the 2t minus 1 minus n choose 2 k over n to the t should be at least k. And k is n to the 1 minus epsilon. So this is, okay, let me just plug it in. So 2 epsilon to the t times n minus n squared. I can bound this from above. This is n to the minus epsilon t. Should be at least n to the 1 minus epsilon. Right? Just plugged in the numbers. Tell me what value of t to take. To make this true.
Maybe like epsilon be less than 1 or something?
Right, so when epsilon's very small, then this is like n squared. It's beating this is like n. That's bad. So we really like this exponent to be less than 1. So we want epsilon t to be at least 1. Well, let's just make it 2. Who cares, right? So epsilon times t is 2. This term disappears. This is all just some constant times n, and this is something much smaller than n. So we won easily. So we take t to be, let's say, 2 over epsilon. And for the pedantic people, it's an integer. Okay? So to apply this, it's super simple. You decide what you want. That tells you A, R, and S. You just plug in the numbers and find a t that works. Okay. We have half an hour left, and there are 2 choices. I could do more applications of this, so you understand it better, or I could do a very fast half hour on either the Janssen inequalities or the Lovász local lemma. So let's have a vote. So I don't really mind, and I can't tell from your faces what you want. So for people who are bored of this and want to do something else, you can vote for either Janssen inequalities, which we mentioned several times in various talks, or the Lovász local lemma, also mentioned various times in talks. So who votes to do just applications of this and nothing else? We have like 3 or 4. Who votes to do the Janssen inequalities? Ooh, quite a few. And who votes to the lowest local lemma? Ooh, we have a lot. I could try and do both. That might be a challenge. I think the lowest local lemma won. Okay, let me attempt to okay. Maybe I'll tell you the statements of both of them, and without proving them, and then we'll maybe manage a little application of each. So, what is the lowest local lemma? The lowest local lemma basically tells you, so a lot of the time in this course, what have we been trying to do? We've been trying to show that something exists. We want to show that with positive probability, so we define some random distribution, the probability distribution, and we want to show that with positive probability something happens. And basically, every time when we've managed to do it, we've shown that it happens with very high probability, or we've shown, the expectationally something, so you have positive probability. The lowest local lemma is a way of showing that things occur with positive probability even when they're super, super unlikely. Okay? And in a very general context. So, what is the statement? So we're going to let E1, I'm going to call them B1 because they're bad events, B1 up to Bm, the events in some probability space. So what you should keep in mind is something like we've taken a random coloring of the edges of some graph, and there are various substructures you want to avoid, like maybe a red, blue, green triangle or something. Okay, and these are all the different places it could happen. Right, so each BI is a particular bad event that we don't like. Okay. And let G be a dependency graph on these events. So basically what this graph is saying is you draw an edge between two events if they depend on each other. Okay? It's not exactly that. It's a little bit more complicated. But you should think about it in those terms. Okay? For the applications we'll see, it's basically just that. Okay? So two events are joined if they depend on each other. And if they're not joined, they're independent. So if the probability of the bad event BI is at most 1 over e times the maximum degree of this graph plus 1 for all I, then the probability that none of the bad events occur is positive. Okay, so what is this telling us? You've got a bunch of events. Each one is, none of them are super likely, but there could be lots of them. There could be really a lot of them. Okay, so maybe each one has probability 1 over 100, but you've got m of them, 10 to the 10 to the 10. So the expected number of them that occur is extremely high, right? But we would like there to be some chance that none of them occur. If they were completely independent of each other, we'd be happy, right? So if the events BI are all independent, then the probability that none of them occur is equal to what? Just the product of the probabilities that none of them that they don't occur, right? The product, like if they're all independent, you just multiply the probabilities. So as long as none of them is certain to occur, this is greater than 0. Right? So for independent events, this is trivial. What it's saying is you can allow some dependencies. They don't have to all be independent. Some of them can depend on each other, as long as each of them doesn't depend on too many others. If each of them only depends on delta others, then as long as your probabilities are at most something like 1 over delta, you're still okay, even if the number of them is huge. Please.
I'm a bit confused
Yeah.
by the notation using sign probability intersections of complement of all.
Yeah, so I mean that none of them occur. So for each one of them, BI complement occurs, meaning BI does not occur. Sorry, BI complement is, BI did not occur. This bad event did not occur. So this is just saying, B1 did not occur, B2 did not occur, B3, none of them occurred. None of the bad events occurred, has some chance of happening. Yeah, thanks. Yeah, so here's perhaps a nice application. Can I do this? Do I need Chernoff for it? What's a good simple application I can give you? So we saw that if H is a k-uniform hypergraph, then with fewer than 2 to the k minus 1 edges, then it must be 2-colorable. Right? So using this, what can we prove? So now we can prove that. What do I want to say? If the maximum degree of this hypergraph is at most 2 to the k minus 1 over k, maybe we'll put a factor of 3 or something, then we get the same thing. Right? Okay, so do you remember this? We did this in the first day. All we said here was randomly color the vertices. Each edge is monochromatic with probability 1 over 2 to the k minus 1. So the expected number of monochromatic edges is smaller than 1. So with positive probability, there's no monochromatic edge. So there exists a coloring. There's a proper 2-coloring. A coloring of the vertices with no monochromatic edge. Right? That was maybe our second application on the first day. Okay? Now we can strengthen it a lot by saying, look, you can have way more edges than this, but as long as every vertex is only in few edges, then we're happy. So why is that? Let's do the proof. Proof. Okay, so let's just randomly color the vertices again. Randomly color the vertices. Red and blue. Okay. And what are our bad events? Our bad events are that the edges are monochromatic. Right? That's what we want to avoid. We would like a coloring with no monochromatic edge, hyperedge. It's okay? We're nodding? We look confused. If you're confused about the statement, then you really definitely should complain. Okay? If you don't complain, I assume the statement is clear. Okay, so B1 up to Bm, the events, so the bad events, okay, where Bi is the event, the edge I is monochromatic. Okay, this is a collection of events in some probability space. So we need to work out which ones depend on which ones, and also what the probability of the event is. So what is the probability of each bad event? What's the probability of this bad event? Yeah, just the same as it was before, right? 2 to the minus k plus 1. Right? All the vertices in that edge having the same color. Okay, and what about the dependency graph? So here's an edge I. Which other events depend on Bi? Suppose you know whether Bi occurred or not. Which other ones does it tell you something about? Yeah, every edge that intersects this one. Right? And how many of them are there? Well, yeah, k times delta. Right? The delta of G is, at most, k times delta of H, which is at most 2 to the k minus 1 over 3. Right? I now claim we're done because, right, 2 to the k minus 1 over 3, okay, the plus 1 doesn't really matter, e is less than 3, this is giving something bigger than 1 over 2 to the k, okay, 2 over 2 to the k, right? So this holds. So this holds. What does that tell you? Tells you with positive probability none of the bad events occurred. That is, there exists a coloring with no monochromatic edge. Okay? So this is very powerful when you have a huge number of events that are almost independent of each other. Right? You get something much better than you get from just this simple first moment. Okay. Now again, two choices. Now you've seen this. So I can prove this. I'll prove actually a more general version, and then finally give an application of that to R3K. Or I can talk about the Janssen inequalities for 15 minutes. Who votes for talk about this for 15 more minutes? Who votes for talk about Janssen inequalities for 15 minutes? Okay, that one won. Good. You're going to see a little bit of everything. It's great. Okay. Then at least you know what it is, right? Okay. Okay. Right. So, suppose we want to know actually the probability that there's no triangular random graph. Okay? Suppose you want to know it much better. The Janssen inequalities give us a way of controlling it much more precisely. So, first, Okay, so what is, I'm going to do a warm-up first. What is the probability that GMP contains a triangle? Well, let me instead find the probability it doesn't contain a triangle. Here's a way of doing it. We could list all the triangles in the complete graph, and we could go through them one by one, asking, are you triangle? Are you in GMP? First one says, no, I'm not in GMP. Great. Go on to the second one. Are you in GMP? No, I'm not. Go to the third one. Third one says, yes, I am. Okay, we're done. We lost. Right? The only way for not to have a triangle GMP is for every single triangle to say no. Okay, so this probability is just the same as the product from I equals 1 up to n choose 3 of the probability that triangle TI, let's list them, triangle 1 up to triangle n choose 3, is not in GMP except we already have some information by this point. By the time we ask triangle I, triangles 1 up to I minus 1 have already said no. So this is conditioned on triangles 1 up to I minus 1 are not in GMP. Okay? They're not independent. We already have gained some information. Right? However, did this information help or hurt us with this probability? How does this affect this? Right. The fact that a bunch of earlier triangles were not present doesn't mean you have none of the edges, just you didn't have all of them. That's giving you some negative information about some edges. It's sort of pushing the number of edges down. And negative information about edges can only make this event more likely. Right? This is also a negative event. This has not happened. It can't make it more likely. Right? So this is at least the product of the probabilities of the TIs not being in GMP. This is now just exactly 1 minus p cubed. It's now equals 1 minus p cubed to the n choose 3, which is approximately e to the minus p cubed n choose 3. Okay? This is the only step that you might be a bit concerned about, and this is called Harris's lemma. Okay? And if you're a bit concerned, I think it's fair enough. Right? It takes a little proof. Okay? But it's not so difficult to prove, actually, in much more generality. Okay? What it's basically saying is negative events help negative events. Right? Positive events help positive events, and positive events hurt negative events. Right? So positive and negative means increasing or decreasing, technically. Okay. An observation about this thing. This is p cubed n choose 3. That's the average, the expected number of triangles, right? This is saying the probability of having no triangle is at least e to the minus the expected number. For those who have done a little bit of probability, you might recognize e to the minus the expectation as being the probability a Poisson random variable is 0. What it's saying is that this probability is dominates probability in a Poisson random variable. Okay. The Janssen inequality is going to tell us if the events don't depend on each other too much, this is a good approximation. It really looks like Poisson. Okay. So now that we're warmed up a tiny bit, let me state the general version. Or the Janssen inequalities properly. So you should always be thinking triangles in a random graph. Okay? The statement will be more general. Think of them as triangles. So here's the setup. we have m subsets of some ground set n. So think n is n choose 2, it's the edge set of the complete graph, and the ai are the triangles. Maybe even think of n as being literally the edge set of the complete graph. Okay. We have a set S, which is a p-random subset of n. Right, so we can take each element of 1 up to capital N independently at random with probability p. So S is just the same as GMP. Right? We're picking each edge independently at random with probability p. That's what I mean by p random. Okay, so S is just GMP. And BI is the event AI is contained in S for each I. So BI is the bad event. This particular triangle is present in the random graph. Okay. Let's let mu be the sum of I of the probability of BI. This is just the expected number of bad events that occur. Okay. And finally, delta is going to be something like the variance. It's the sum over I tilde j of probability bi and bj both occur, where this means they depend on each other. So this means that ai and aj intersect each other. Okay? So we just have, we're looking at triangles of a random graph. We've got the expected number of triangles and the variance. So this thing, for us, would be p cubed n choose 3. And this thing we showed is at most p to the 5 n to the 4, right, for triangles of the random graph. That's what we proved maybe end of second class. Okay. Nearly there. What the Janssen inequality say they say the probability that none of the bad events occur is at most, so e to the minus mu is the best we can possibly hope for. Right? That's what Harris's lemma tells us. We can't hope for better than that. The error is plus delta over 2. Okay, this is great as long as delta's smaller than mu. So, but what if delta's bigger than mu? Then we can get something still pretty good, e to the minus mu squared over 2 delta. So what this is telling us is the probability that we have no triangle is actually very small when the expected number is large. So far, all we managed to do was use Chebyshev's inequality, which gave a very weak bound on the probability. This gives the correct bound. Okay? This turns out to really be the truth. So this is telling us exactly the probability that none of our, well, not exactly, but sort of up to the right order of magnitude, the probability that none of our bad events occur. I have 6 minutes to give you an application. So, okay, I'm going to give you a simple application. So, theorem, if P is a constant over n, then the probability that there's a triangle in GMP converges to 1 minus e to the minus c cubed over 6. Okay, so this tells us inside this window, someone asked the other day what happens inside the window, this tells you what happens to the probability. I wonder if I should actually do this or just maybe leave it as an exercise. Okay, I'm going to give you three applications, and they're all going to be exercises. Okay? So using the Janssen inequalities and Harris's inequality, which says this is at least e to the minus mu, which is Harris, then you can prove this. Here's another thing you can prove. The probability that there's no triangle in GMP is at most e to the minus constant p cubed n cubed, if p is at most 1 over root n, and at most e to the minus constant pn squared, if p is at least 1 over root n. Okay, so we already basically saw this first one. So this p cubed n cubed is it's mu, right? It's the expected number of triangles. And so to prove this, all you have to do is show that delta is smaller than mu up to when p is smaller than 1 over root n. And then when p is bigger than 1 over root n, you use this instead. Okay? We already bounded delta, right? It was p to the 5, n to the 4. This is very simple. But this is quite a nice illustration of what Jin Young was talking about. So you remember she was talking about these covers of the property of all the triangles, right? She would say the minimum weight cover of your property determines the threshold. And the stronger conjecture they're trying to prove was saying that, oh, actually, maybe the best thing is just to take all subgraphs. So for a triangle, what are the two possibilities for a cover? If you're going to cover all triangles, you could take all triangles. That would cover it, just the same thing. Or you could take all edges. Right? If you take every single edge, every triangle contains one of these edges. If you take all triangles, then every triangle contains one of these triangles. Those are the two most natural covers for the set of triangles. This one is the cover that's the set of all triangles. And this one is the cover that's the set of all edges. Look, there are pn squared edges. Right? So these two most natural covers appear already in this theorem as the dominating term in the probability you have no triangle. And what's happening here is really just your most likely way of having no triangles is just not to have any edges. Right? To have way fewer edges than you expect. Right? That's what this is saying. Right? This is saying happen to not have any triangles. This is saying just don't have any edges. Okay? So all of these things that you've been seeing during the week in all these talks, they're all connected behind the scenes. Right? Like it's not a coincidence that these things the same things keep coming up. There's something like deeper going on. And the final application, which is a little bit hard to find, but was actually the original motivation for the Janssen inequalities, is the following theorem of Bolabash from 88 that says that the chromatic number of the random graph G1/2 is equal to 1 times n over 2 log to the base 2 of n with high probability. So on the example sheet, I asked you to prove the easy bound, the upper bound on this correct number, where you just look at the size of the independent set. To prove the other direction, let me give you a hint. Here's how you find a coloring with this many colors. So the independence number is basically this. Okay? This is the independence number. So what it's saying is you can properly color the random graph very efficiently with independent sets that have size roughly with color classes that have roughly the maximum possible size. So here's the strategy. Pick a large independent set, give it color 1. Look at what's left. Pick a large independent set, give it color 2. Continue. So you have color K. And then there's some m vertices left over. Okay. I want all these guys to have size basically 2 log n, like the maximum. And then once you can't find that, I'm just going to say there's not many vertices left, so I'm just going to color these all different colors. Okay, so the claim is that you can cover almost all the vertices with these very large independent sets. Why is the Janssen useful for this? Well, the trouble with doing this is, once you pick the first independent set, the distribution on the rest of the graph is no longer GMP. You've messed up the distribution by choosing this large independent set. You've changed everything, and suddenly you can't calculate. So what you need is, from the start, that every set of vertices bigger than this M contains a large independent set. Right? You don't just want GMP to have one large independent set, you want them to be everywhere. And in any large set, you can find one. How can you prove that? Well, you can show that the probability that M vertices fail to have one is super, super tiny, and then take a union bound over all subsets of size M. How are you going to prove the probability is super, super, super tiny? These functions are super, super tiny. Okay? So apply the Janssen inequalities to show the probability you fail to find an independent set in M vertices is really small, therefore you find them everywhere, therefore this greedy argument works. Okay? So, I know that was extremely fast, but hopefully today you saw a little glimpse of 3 different very important theorems and techniques in probabilistic combinatorics. I hope you go back to your universities and demand that your professors teach you about these things in much more slowly and in much more detail. Anyway, and thanks for your attention.